All right, so the topic technically is this: rigid motion in a plane. That's what we're going to talk about. But what I want to maybe just preface this a little bit by talking about why this is important. What does this stuff do for us? Rigid motion in a plane, we're going to refer to some different kinds of transformations, and a lot of you have already started on Chapter 7, so you know what we're talking about. But a lot of the things we can do geometrically in the XY plane, for example, we can do reflections, right? Even though the stuff we're doing is really obvious visually, we're taking something and we're reflecting it over a line, and we'll talk about that in detail today. It relates to some things later on in life that just aren't so obvious that you can do. It leads into a talk about symmetry, and we'll end up today talking about reflections and talking about reflective symmetry. We'll get on to rotational symmetry later. But reflective symmetry, it'll be real obvious to you, is related to lots of other kinds of symmetry that maybe aren't so obvious. When we look at the world and we try to describe the world around us, some of the stuff is clearly geometrical. I mean, there are things, if you look at, at molecules and at soap bubbles and things like that, yeah, we run into shapes that we see in geometry. But we can have symmetries that aren't necessarily spatial. For example, imagine, you've got to use your imagination. Run this movie in your mind for a second here. In fact, pretend somebody's videotaping this. Say I've got a ball and I throw it up in the air and I catch it. Throw it straight up in the air and catch it. If I videotape that. If I show you a video of the movie, do you know if I'm showing the movie in forward motion or if you're watching it in reverse? Can you tell? There's no way to tell, is there? Unless I'm talking or something, my voice would sound kind of weird, it's going backwards. But if all you're seeing is just the picture, you can't tell. And so, now, think what that means. That means that if I were to think about the time from when I throw the ball up to when it hits the peak, compared to the time that transpires from the ball going from the peak back down to my hand, the motion of the ball is symmetrical with respect to time. How about that? Right? The time from here to here ends up showing us the same movie in a reflected version as the time from here back down to my hand. So the point I'm making there is that you can extend these concepts of reflection from just beyond the stuff we're doing in the textbook to other concepts, like being, literally symmetrical with respect to time. If you want to go further than that, you can even look at particle physics, and you could talk about weird symmetries that don't show up in normal life. You could talk about symmetries with respect to probabilities of an electron being here or here. Turns out that even though it can never go from here to here through space, like we could, for example, we could have an atomic distribution that was centered on a vacuum. So the electron could never be in the vacuum, let's say. We put up an impenetrable barrier there. The electron a single electron can still buzz from one side to the other without ever going in between the two places. It's very bizarre. Quantum mechanics is weird, but it's the way the world works on very small levels. The probabilities of where the electron is going to be. There are literally symmetries with respect to the probabilities. There's all kinds of weird symmetries that we can talk about in nature and physics and science and in math that are much different than what we're talking about right here. But this is the foundation for all of them. So there's more to it. We're demonstrating one application that we could go much further with later on if we wanted to. All right, we're going to start off talking about rigid motion in a plane. Now, it's really important that we understand. One thing that's nice about the terminology and the vocabulary that goes with geometry is it's very descriptive. If you remember the words literally tell you what you're doing. What does rigid mean? That's a word we use sometimes in just normal everyday life. What's rigid mean?
Like exact.
Okay, exact. Yeah, we could say, there's a lot of ways we could use it. If someone has a rigid personality, I guess they're very by the book, right? That's one. But I'm thinking more along the lines of if I'm looking at some objects. If I have one object that is pliable and one object that is rigid, what's it mean to be pliable? Hannah, you have an idea? Distinct. Okay, that's one. That's good. What else?
Pliable means you can bend it. So
Yeah, it means bendable, sure, but if it's rigid, is it bendable? No, it's not bendable. If it's rigid, it's in place. I mean, it's I'd break it, right? If I tried to distort it, it would break. It wouldn't bend. Yeah. Movable. Okay, now these are going to be movable, but when they're movable, the question is, after we move the thing, has it been bent and squeezed, or has it stayed the same? And the kinds of motions that we're talking about are motions where the object doesn't get changed, doesn't get distorted. The object itself is going to look the same before as it does after. They're superimposable. We're going to find out that they're congruent. Okay? These rigid motion means that what I end up with after the change is congruent to what I had before the change. Okay? Does that make sense? So not pliable, it's rigid. Okay, there are three kinds of transformations that this is all based on, and they're pretty simple. Figures in a plane can be reflected, and we'll talk about that in more detail today. They can be rotated. We'll just get introduced to that today and go into more detail later. Or translated. And that just translation, by the way, if we say translated, that's a real fancy word in math for slid. Okay? If we translate something, we're just sliding the puzzle piece across the page. To produce new figures, we can do all three of these things. Okay, the new figure, now this is the part we got to be careful about. The new figure is always going to be called the image. Okay, that's what we end up with, is the image. That's the result of the transformation. What we start with is called the pre-image. Now, pre means what? Before. Sure, if you're watching a preview of a movie, that's something you watch before you are able to watch the movie. The movie didn't come out yet, right? So pre means before. So the pre-image, what you start with, image is what you end up with. Okay, like we say, three basic transformations are reflections, rotations, translations, or combinations of the three. We could do, later on we'll talk about what happens if we link them together and do more than one thing. Combination of transformations. But for each of these, we're always going to start with a pre-image and then transform it to create an image. Now, in the next slide, we're going to get our first taste of this. Pay attention to the color here. The blue figure is always going to be the pre-image. So that's what we're starting with. And then the red figure, is going to be the image. Okay, so we're starting with blue, ending with red. Okay, so a reflection. We can see that's a reflection, right? We started with the blue figure. We folded the paper. And the way to think about this, when you're talking about reflections, the way I've said this before, and you might think it's kind of dorky, but I think it really works, is imagine that I draw the blue F in wet ink, and then I'm going to fold the paper and make an imprint. And that's going to be my image. And my original writing is the pre-image. The imprint of that from the wet ink is the image, right? Now, what do you notice about the reflected letter? Because it starts off looking like the letter F, doesn't it? What do you notice about the image of that pre-image? Yeah, it's looks goofy, doesn't it? It's been inverted, right? It looks backwards. Now, wouldn't you agree that it still overlaps perfectly with the original? So it is congruent, right? But it's been inverted. Okay? We'll get back to that. Rotation. Now, a good way to think about rotation is imagine that I'm going to draw the blue, say this is a transparent sheet of something, plastic that I'm writing on. I draw the blue F on the transparency and I put a tack in the transparency. It's on a bulletin board or something, right? I put a tack right there and I spin this thing. That's a rotation. Okay, wherever I end up after I spin it, that's the image of my pre-image. Okay? So if we wanted to track the progress of maybe one point, of one vertex, we could take, for example, this point, right here, how about? Okay. So there's a point on the original pre-image. As I rotate this thing, doesn't it kind of just describe a little arc like that and ends up right there? Does that make sense? So what would you say if this is the angle, or excuse me, if this is where the tack is? So it's the center of rotation, we would say. We'll get into that in more detail later on. What's the angle that we rotated the transparency there, do you suppose, roughly? It looks like about 90 degrees, doesn't it? We started right there. There was our, that's how we walked from the tack up to that point, and we end up with our image being right there. So that looks like about a 90-degree angle, doesn't it? Right? So 90-degree rotation about that center. Okay, the center being right there. Now this time, if we look at the rotation, did the F get messed up? Started off looking like a real F. Did it end up looking like a real F? Yeah, it did, didn't it? Right. So things didn't get inverted for the rotation. They did for the reflection. Now, translations are the easiest probably to visualize. Translation is just sliding. I've just got a blue puzzle piece that's my pre-image. I'm just going to push that along the plane to create my image. Right? So translations are simple to visualize. I'm just sliding it. Okay? And notice that the F doesn't get messed up there either. That inversion of the picture is a specific property of reflections. Just like if you look in a mirror. If I hold up writing in a mirror, it looks goofy, right? It looks backwards. Or if you look in a mirror, you don't see what other people see. Actually, you see the mirror image. You're pretty used to it, but other people see you a little differently. If you look at a picture of yourself, it's different than what you see in the mirror. All right. How do we say this stuff? Okay, well, one way we do this. Transformations involve some labels. We're going to start off with something. Maybe it's a triangle, maybe it's a letter, who knows. But we're starting with some kind of a thing that we're going to transform in one of those three ways we just talked about. The way we say that, every point that starts off on the pre-image is going to be written normally. Like, for example, point A, let's say, is a vertex on the triangle that we're transforming. After we move it, after we transform it, so the pre-image is A, the image we're going to write as A prime. We're going to put a little tick mark right here. Okay? And we literally read it as A prime. That means it's been changed. When you see that prime, it means that's the product of the result of some movement of some kind, some transformation, reflection, translation, or rotation. Could be any one of them. But we've transformed this original pre-image to give us that. So that's what the prime means. The prime goes with the image. The unprimed version is the pre-image, always. Okay, so now let's study this one here a little bit. Don't jump to any conclusions. You got to look at these a little carefully sometimes. First of all, I want you to name and describe the transformation. What kind is it? Is it rotation, reflection, or translation? Okay, it's a reflection. You got to look a little bit carefully because it almost looks like an isosceles triangle, doesn't it? Right? If it were isosceles, you know what? I'm gonna make that point real quick. Let's see. If I go to here, I think I can play with my toys. This will be kind of fun. Let's get a triangle. Okay, so here's a triangle. It's isosceles, right? Now, what if I want to... What do I want to do with this? I want to do this. I want to reflect it. So I want to go like that. Now, I reflected it, didn't I? But because those are, that's an isosceles triangle, does that have to be a reflection? That could also be a translation, couldn't it? Either one would be fine there. Because if I slide it, they overlap perfectly. Or if I reflect it about some line in the middle, they would overlap perfectly. Right? But if we look back at our what we've got going here, it's a little bit different. This isn't isosceles. Notice that if you look closely, AB is a little bit steeper than BC, isn't it? Slope's a little larger. Okay, so then we can see that AB maps to A prime, B prime over here, doesn't it? Right? That has to be a reflection then. Okay, if I slide it, they won't overlap perfectly. So describe it. Describe that. It's a reflection. But if we're going to say it's a reflection, we got to say it's a reflection in what line? Where, in other words, if I'm going to draw the blue triangle in wet ink and fold the paper to create the red triangle, when I unfold the sheet, where's the crease? What's the, describe that crease? It's the y-axis, isn't it? Right? So here's the axis of symmetry. Okay, or the axis of reflection, whatever you want to call it. That's going to be it. Now, if I could call it the y-axis, and that's fine. What else could I call it? If I want to come up with an equation of that, what's the equation of the y-axis? The book asks for that quite a bit. They want to know what's the equation of the line of symmetry. If it's a vertical line, those are a little strange. Vertical lines, how did we write the equation of a vertical line? X equals something, right? It doesn't fit the y equals mx plus b scheme because there's no slope. If it's a vertical line has no slope, right? We can't put an m in. So when we want to write the equation, we have to write x equals and then fill in what's x always equal to. Every x coordinate on this line, or every coordinate on this line has an x value of what? And the easiest one to think of is just where it crosses the x-axis. What's the x-coordinate of every point on the y-axis? 0. Sure. They all have coordinates 0 something, right? So it's x equals 0. That's how we could describe this. If we want to be the most accurate, we'd say that it's a reflection in the line x equals 0. Okay? Name the coordinates of the vertices of the image. Well, we don't have to name them all. Let's pick one. What are the coordinates of A? What are the coordinates of A? -4, +1. Okay? Okay, what are the coordinates of A prime? 101. +4, +1. So there's an important connection there. What do we notice about those coordinates? If we reflect something in a vertical line or over a vertical line, what are some characteristics of that? That's one thing we know. What about the y coordinates? There?
They change. Well, the y stays the same.
Y always stays the same, right? Because if we're reflecting over a vertical line, that means that all of the motion is horizontal, isn't it? Right? Does that make sense? So the vertical coordinates of every point, pre-image and image, will always stay the same. The x-coordinates are going to change. Now, if it happens to be the y-axis, if it's the y-axis, we've got some interesting symmetry there, because then we know that the pre-image A had to have been just as far to the left as the image A prime is, right? On that grid. And so we notice that they just end up being opposites. You've got to be a little careful with that, though, because what if the line of symmetry hadn't been the y-axis? Then the x-coordinates would have necessarily been opposites. Right? And you'll see some examples like that. But the y-coordinates would always be the same. Okay? Is ABC, triangle ABC, congruent to its image after reflection? Yeah, of course. It's an isometry. Or we haven't said that word yet. It's a rigid transformation. Right? It's a rigid transformation, so nothing is getting bent or squeezed. Okay? So we can skip through that. We just did that. Okay, there's the word. Isometry. Isometry is just a shorter word for rigid transformation. What does that mean? It says exactly what it means. In math or in anything, iso is a Latin root. What does iso mean? Same, like isosceles, same size, right? Iso means same. And every time you use the root meter, that always has to do with what? Yeah, measurement. Right. So meter means measure, metry, or we added try at the end means measurement in general. So it means same measure, same measurement. All the measurements would stay the same. All the angles, all the side lengths have to stay the same in an isometry, which is just a rigid transformation. If it's not being squeezed or bent, all the measurements would stay the same, wouldn't they? So let's take a quick look at some of the properties of that. Okay, does that appear to be an isometry? The blue pre-image and the red image? Yeah, what kind? What kind of isometry? An isometry is just a rigid transformation. What kind of rigid transformation? Yeah, it looks like a reflection, doesn't it? Good. Yeah, they definitely look congruent. What about this one? No. It's not. It's not, is it? The image is definitely not congruent to the pre-image. It looks smaller. It looks like it's been slid but also shrunk. Right? So that one wouldn't qualify. Okay. What about that one? That looks good, doesn't it? What kind of isometry would that be? Rotation. Good. About the center, right there. Okay. And then that one. That looks good. What kind's that? Translation. Okay. Now, one other thing that's important to note here. How do we say this? Okay, we could say, how would we say this? We'd say that triangle ABC is mapped onto triangle DEF. That's kind of an awkward way of saying, but that's the mathematically preferred way of saying that. ABC is mapped onto DEF. Now think about that. That's mapped. There's a way you can remember this because it correlates to the way we use the word map in real life. If you want to map something out for somebody, aren't you giving them precise directions? Isn't that what it means to map something out for somebody? Where's your house? Here, let me map it out for you. Right? That's what you're doing. That's what we're doing here. By using this transformation, we're going to provide some precise directions for taking the original pre-image and getting it to the image. Right? So it's mapped onto that location. Now, something is true here that was true for us earlier in the year, so this isn't new. Remember that when we talked about congruent triangles, we had to be very careful in our congruent statements, we had to be very careful to line up corresponding parts. Right? For example, if we had something like this, say we had a triangle ABC and triangle HWM. If I want to make a congruent statement about those triangles, let's say we know they're congruent, I could say triangle ABC is congruent to triangle what? Which point does A line up with? Vertex A corresponds to what vertex? W, it looks like. Those two go together. Maybe it helps if I do that. So W, and then E looks like it's right down there, so that would be H. And then finally C lines up with M. So that's the way I have to say it. Right? I have to get that correspondence in there. Same thing is true when we talk about transformations. Point B, pre-image B, maps to image E. So the B and the E have to line up together in that statement, right? What's the arrow mean? Well, the arrow is our shortcut way of saying maps onto. Okay, that's our little symbol for triangle ABC is the pre-image, and it gets transformed into triangle DEF. Okay? Just an arrow. Tells us the direction goes from the pre-image to the image. Okay. So, we can skip. Okay, so that's our introduction to all three. I want to just real quick I want to focus on reflections in a little more detail. And that's all we'll do today. So, reflections. We want to be able to identify and use reflections in a plane. And we want to see, my other goal here is I want you to be able to see the relationships between reflections and line symmetry, or reflective symmetry. That's what we'll end up with. Okay. We've already talked about this a little bit. Let's get a little more specific. A reflection in a line M means a transformation over that line, right? So I need to label the line here, but this is line M. So that's the line of symmetry. Okay, now I want you to come up with a relationship for me here. I want to know what are some of the relationships between pre-image P. So this is, let me draw that a little bigger so you can see it. There's pre-image P, and here's image P prime. What are some of the relationships? And let's try to describe these. We can start off describing them casually, but let's see if we can attach some mathematical statements to these and make them rigorous. What are some of the things that must be true there? What do you think? Throw some things out. The line of symmetry M and the points P and P prime, the pre-image and the image. What do you think there?
Both P and P prime have to be equally distant from M.
Ah, okay. So if we were to, for example, let's put a point there. The point that would be the intersection of segment P prime. Let's draw that even. There's segment P prime. The intersection of segment P prime with line M, if we call that like Q, what they're saying, this makes sense, is that this distance, PQ, would have to be the same as P prime Q, right? Doesn't that make sense? It has to, right? They have to be equidistant from the fold in the paper, sure. Okay, what else? Any other relationships that you can think of between the line segment, P prime, and the line of symmetry M? Yes, ma'am. Perpendicular. Very good. Right? They would have to be perpendicular also. So we could say then that the line of symmetry, the line of reflection, whatever you want to call it, is the perpendicular bisector of the segment connecting the pre-image and the image, P prime, right? Okay? If P is not on M, if the point is not actually on the line of symmetry, then M is the perpendicular bisector of P prime. It has to be that way. Okay? Now, what if P is actually on M? What if the point that we're using, and remember, think of the ink. I make a wet ink dot on P, I fold the paper on line M, and I create the image P prime, right? What if the ink dot, if the point is actually on the axis of symmetry, on the line of reflection, or line of folding, whatever, it's all the same stuff, isn't it? What's going to happen then? Imagine that. What did I create? A crease. Where did the point go? The point that started on the fold. It's kind of, but now, sure, now the ink dot has some size to it, but mathematically, how big is a point, really? It has no size. So where's the location then of P prime? The pre-image was on the fold. Where's P prime?
On the fold.
On the fold. They're right on top of each other, aren't they? They're the same thing. Okay? So in the event that P is on the line, well then P prime is the same place. Okay, they map to themselves. Okay, what about this? Real quickly here. What if we want to, you're going to ask me to do a lot of this kind of stuff on the assignment. Graph these given reflections. Let's take point H with coordinates 2, 2. So over 2 and up 2. Right? And let's reflect that in the x-axis. Okay? So then, does it make sense that it's going to end up getting, if I fold the paper, around that horizontal crease, that H prime is going to be down there? Right? Doesn't it make sense that this distance right here is the same as that distance right there, right? So you could predict the coordinates pretty easily, couldn't you? Without even looking at the picture. Right? If I'm folding it about a horizontal axis, all of the reflection has been vertical then, right? So we know right away that the x coordinate of H prime has to be 2, doesn't it? It's not going to change. The y coordinate in this case, that'd be -2, right? What about this this one right here? What if we take point G that has coordinates x equals 5, y equals 4, and we reflect that in the horizontal line, y equals 4. So here's the fold in green. There's the dot of ink. Where does it end up? Where's the image? Where's G prime? Same spot, right? It's on the axis of symmetry. It's on the line, so it doesn't move at all. Okay? Okay, and so we see this property in general. I don't want to get too hung up on this. We've talked about that a little bit. That's all I'm going to say about that. Okay, reflection is an isometry, just, like we've talked about. Here are really the different cases you could see. If we take a line segment as an example, that's an easy thing to do. If we take line segment PQ and we look at all the different scenarios for what could happen if we reflected over a line. Well, the most obvious is probably the one where PQ, the blue pre-image, is completely on one side of the fold, the line of symmetry. And that's the one we've looked at already quite a bit. Then the image, P prime, Q prime, ends up being completely on the other side. Right? Make sense? Now, what's going to happen, though? I want you to visualize this if you can. This is an important skill you develop in geometry. Try to think of this in your mind. Draw yourself a picture. What's going to happen if the blue segment actually, so the pre-image, crosses the line of symmetry, crosses the fold? What's going to happen when I fold the page and create the image of the wet blue line? What do you think?
The image is going to cross the pre-image.
Yeah. The image is going to cross the pre-image, isn't it? Right? Let's look at an example. So what if here's the pre-image in blue? When I fold the paper, look, the image I create is going to have crossed over the pre-image, isn't it? Right?
What do you mean, like they're going to lap over each other?
Yeah, they'll overlap each other, right? Because if this is the fold, there's the line of symmetry, then they're going to cross over that line of symmetry symmetrically, right? Doesn't that make sense? Because the part of the original pre-image that was on the right is going to make an imprint on the left, and vice versa.
So they both still exist, they don't combine, right?
No, they don't combine. The only place where they combine, they overlap at that one point. Right? But otherwise, they're separate. Okay? Now, what about this one? I mean, this is, no big deal. But what if you get an example where the blue segment has one endpoint on the line and one endpoint off the line? Well, then when I fold it, aren't I going to get the point that was on the line is going to overlap? Everything else will be on the opposite side. No big deal. And then maybe the last case would be, what if the blue pre-image is perpendicular to the axis? Well, then so is the red image. No big deal. Okay, so now lines of symmetry. Last thing, everybody focus up here real quick. We got really 2 more slides and then we're done. I want you to pull this in though, because this is the part that I honestly think, in a way, is the most interesting. Here's that symmetry thing we're talking about. Different kinds of symmetry. We'll look at rotational symmetry later, but today we're going to look at just folding symmetry, at line symmetry. If I take this hexagon, 6-sided polygon, would you say it's symmetrical? Yeah. It's a little bit symmetrical, isn't it? It's a little bit symmetrical because if I fold the paper right down the middle, I can get it to overlap perfectly, right? Are there any other lines I could draw on this one that would make it do that? See, I think that it depends how exactly this is drawn. Potentially, if these angles are congruent, couldn't I also draw one there?
Yeah.
Okay, but maybe they're not. Maybe this angle is a little bit different than that one is. And I think that's what's intended in this drawing. So then there could only be one line of symmetry here, and that's it. Now that's better than none. It's got some symmetry, and many objects don't have any. Could I come up with a hexagon that is more symmetrical than that? What could I do to make this hexagon more symmetrical? Yes, sir. Make it regular. If I want to make the most symmetrical hexagon, let's make it regular. Like that. Look at all the lines of symmetry there. Right? I have a line of symmetry. If I want to, let's say I want to cut through this thing halfway through the flat side, so I could cut through it like that and fold it over, right? Or I could cut through it like that and fold it this way. Or I could cut through it like that and fold it that way, right? If these are just perpendicular to the flat sides of this thing, the straight sides, those would all be lines of symmetry, wouldn't they? Or if I want to, maybe I want to cut it a little differently. Maybe I want to cut it through, let's say, through the vertices. I want to fold it there. That would work, right? Or that would work, or that would work. I got 6 different choices, right? So this is, if I have a regular, see if you come up with a relationship here. A regular hexagon with 6 sides had 6 axes of folding symmetry, of line symmetry. What if we took a regular quadrilateral? What does that look like? What's a regular quadrilateral? Square, sure. That's just a square. So, whoops, wrong one. There's a square. Okay, let's look at the axes of symmetry on this one. Don't I have one right there? Right? Got one right there. And then I could go through diagonally, couldn't I? So I could go through kind of like that, or kind of like that, right? You get the idea. Okay. So what could you tell me in general then? I had a regular fourgon, had 4 axes of symmetry. Regular hexagon had 6. What's the pattern? Yeah, it's the same, isn't it? Okay. So now, not always, but a lot of times it is. But in general, we could say this. We could say if I wanted to build a polygon with tons of lines of symmetry, what would I have to do? Well, okay, I want to get more and more sides, don't I? The more sides I get on a regular polygon, notice what happens. This is a really interesting concept. TJ, you're going to like this. Sure enough, I'm going to show you something. This is cool. What if we do this? What if let's start off with a pentagon, and let's just kind of build ourselves regular shapes, and I want you to see what happens. Okay, lots of symmetry there, right? Looks like I've got 1, 2, 3, 5 of them there, right? 5 different ways I could slice that and make it look fold onto itself. Let's get a hexagon. Okay, whoops. Okay, if I draw it regularly, there's 6. What if I go down to something like this? I think this is, I don't even know what this is. Octagon? Octagon. Okay, good. Now what about, I guess that's as big as I can go on here. What if I had a regular 30gon? That's going to start to look an awful lot like what? Circle. Yeah. As the number of sides of the regular polygon increases, wouldn't you agree that each side becomes smaller and smaller and smaller, and the angle between them starts to flatten out, right? And so it starts to look an awful lot like a circle. If I were to try to draw, for example, on this board, a regular 200gon, I mean, it would look like a circle. You would have a heck of a time even distinguishing it as a polygon and not a circle. So really, a circle, one way to describe a circle, and this is a little bizarre, a circle is a regular infinigon. If I were to let the number of sides of a polygon just increase without bound and keep getting bigger and bigger and bigger, the limit of that, I'm never going to get there, but the limit is I'm going to get shapes that more and more and more closely approximate a circle. Now, how many axes of symmetry, of line symmetry, does a circle have? Yeah, an infinite, because any line, isn't that weird? Isn't that a weird concept? to me, that as much math as I've done, I never really completely get used to the idea that you can take something finite like a circle. I can measure the distance around that circle, and it's a number, right? There are an infinite number of ways to slice that thing, of course, right? As long as the slice goes through the center of the piece of pizza, right? So if I could make a slice right there, I could make a slice right there, and a slice right there, and a slice right there. And I could theoretically cut that pizza up. If I have a sharp enough knife, I could cut that pizza up into an unlimited number of pieces, right? Does that make sense? So I really have an unlimited arsenal of lines of symmetry on a circle. It has infinite symmetry. And you could say that it is the most symmetrical shape, two-dimensional shape possible. Has to be. Okay? All right. Very good.